Hello everyone, today I will work on some exercise problems from this 12.6, only part B, quadratic surfaces. My assumption is the part A, the cylinders already something you can easily understand. Okay, now let's start with, so the way I will explain this, I will not really answer the questions like our textbook wants us to do. Like for example, in part this here, they want us to use traces. No, I will not use traces method, but I try to teach you a way so that you can identify what that surface look like. Okay, and we will not sketch that in details, but it's kind of like some idea only. Okay, so let's see, for example, we do number 12. 9x squared minus y squared plus c squared equals to 0. Okay, and the way I do it will be as follows. Okay, if we look back, this is basically x squared minus y squared plus c squared equals to 0. And then this looks like x squared plus c squared equals to y squared, which if our r squared equals to x squared plus c squared, then this is r squared equals to y squared. Which, if you think about it, this is actually a cone. Think of it this way. Let's say this is the y-axis and this is the r-axis, right? This is r squared equals to y squared in 2 dimensions, right? R squared equals to y squared. And then we rotate that around y-axis. Because x squared plus z squared, the one becomes r squared, right? So if we look back, this is what it looks like. Okay. Now, this 9 here is just the scaling. Okay, that 9 is just scaling. In other words, if we go back to that 9x squared minus y squared plus c squared equals to 0, then it will give us you know what, let me try to see if I can rotate this a little bit. Oh, I cannot. So it will give us a cone parallel to y-axis. And then it looks like this. Okay. Okay. Now, of course, I don't really account for that 9 here, but if you want to see what that 9's actually be, it will make it a stretch, because if we think about this, this is actually x over 1/3 being squared, right? Okay, so we shrink with respect to the y-axis by 1/3. Okay, that's what it looks like, right? Okay, so if we maybe how to, you know what, let me try to make it more accurate then. So let's say this is my z-axis, my y-axis, my x-axis. Okay, now then my graph will be shrink by a factor of 1/3 in the x direction. Sorry, it takes some time to actually sketch it out. So kind of a cone like that. Okay. And let me pull this line here. Make it longer. Yep. Okay, so that's what the cone look like for number 12. Now notice that the way I sketch it, so you will see like if this were h, this is 1/3 of h, because we shrink that by a factor of 1/3. Okay, in the z direction, I mean in the x direction, we shrink that. Now number 14. Number 14, we have 4x squared plus 9y squared plus c equals to 0. Hold on. Oh, I copied the wrong one. 25x squared, 25x squared plus 4y squared plus c squared equals to 100. If I reduce by 100, divide by 100, so that the right hand side, the constant becomes 1. So this is x squared over 4 plus y squared over 25 plus c squared over 100. This is an ellipse, center at origin, stretch in x direction by 2, y direction by 5, and c direction by 10. Okay, that's for number 16. Let's try to graph it. So suppose this is my, oh, yeah, I try to make it nice also at the same time. So when I go in the x direction, only 2, in the y direction, I try to make it as scale as possible, but maybe not enough space. And then it will be 10 here. So it will look like this. Now that's what the graph looked like in the first octant. But then it's supposed to go this way. And then at the back, like this. And of course, supposed to go downward also. Okay, supposed to go downward also. So approximately, that's what it looks like. Okay, that's for number 14. How about number, I think I did number 16 in class. Number 18 is very similar, huh? Is it? Oh, maybe not, huh? Let's see, number 18. Number 18, because we have 16 here, right? Oops. Yeah, we have 16 there. So let's see, number 18. We have 4x squared minus 16y squared plus c squared equals to 16. What will this look like? Oh, I think this will look like, hold on. This will look like, if I divide by 16, x squared over 4 plus c squared over 16 minus y squared equals to 1. If this were my r, let me use, this were my r squared, right? Then the blue color will look like this in 2 dimension. It will look like this, okay, where this is the y-axis and this is the r-axis. You see, right? But then we will rotate with respect to the around y-axis, so it will be hyperboloid of one sheet. Yeah, that will be hyperboloid of one sheet. Okay, now again, the 4 and 6 here, the 4 and 16 here is the scaling, with stretch in the x direction by factor of 2, in the z direction by factor of 4. Okay, so this is hyperboloid in of one sheet, parallel to y-axis. Okay, that's for number 18. Let me go on here. Oh, number 21 to and on, it's basically doing the matching, and I think this is actually more fun. Okay, so we don't really need to know precisely what it looks like, but we guess what it looks like. Okay, so I think we can do it fast here. Number 22, that's 9x squared plus 4y squared plus c squared equals to 1. If I clean up the coefficients, I get x squared plus y squared plus c squared equals to 1. That's a unit sphere, right? Now, when we stretch that with different coefficients, that becomes ellipse. Now, the thing is, we have 2 ellipses here. Okay, which one is the one we want? And that's where we get more detail, right? So we will rewrite this as, x squared over 1/3, maybe, sorry, x squared over 1/3 being squared plus y over 1/2 being squared, and that's c over 1 being squared equals to 1. So it seems like we shrink by factor of 1/3 in the x direction and by factor of 1/2 in the y direction. The c is the longest, so this will be 4. Okay, that's for number 22. Number 24, negative x squared plus y squared minus c squared equals to 1. That's y squared minus x squared plus c squared equals to 1. But if we see this as our r here, it means yeah, it will open this way, huh? Is it right? Hold on, why I feel like this is different from that one? Yeah, that's correct. Yeah, and then we will rotate with respect to the r-axis, the y-axis, right? So it will look like this. So it's hyperboloid of two sheets. Okay, and there's only one hyperboloid of two sheets there. That's number 3. Okay, how about number 26? Number 26, y squared plus x squared equals to x squared plus 2c squared. If I get rid of the coefficients, we basically look at y squared plus x squared plus c squared. That's y squared equals to r squared. Oh, that's a cone, huh? That's a cone. We have that earlier, right? That's a cone. And then we rotate with respect to y-axis. So that's number 1. Number 28, y equals to x squared minus c squared. Next, equals to x squared minus c squared. This is the y. Oh, so what is this again? This is number 5. This is number 5. This is number 5. Okay. Let's see. I happen to see a cylinder here, number 27, and there's only one cylinder here, right? So number 27 is 8. This is number 27. Well, I happen to see it. Okay, number 25, this is y equals to x squared plus c squared, y equals to r squared, right? So it's a parabola. Is it right? It's a parabola. So it's this one. That's 6. It's number 25. Okay, and I think that's good enough, right? Yeah, you can see the rest. Now reduce the equation to one standard form, classify the surface, and sketch it whenever possible. Of course, I don't think I will do that in full. Let's see number 32. Number 32, it's y squared equals to x squared plus 4c squared plus 4. This is y squared minus x squared minus 4c squared equals to 4 divided by 4. So that's y over 2 squared minus x over 2 squared plus c squared equals to 1. Now the reason I write it like that so that we see this, the basic form of this y minus r squared equals to 1. If this is the y, this is the r, then it opens this way in the y direction, right? Okay, so when I rotate that, that's hyperboloid in 2 sheets. That's hyperboloid in 2 sheets parallel to y-axis. Okay, how about number 34? Yeah, we have a lot of completing squares here. Y squared plus c squared minus x minus 16y minus 4c plus 20 equals to 0. So I have 4y squared minus 16y plus c squared minus 4c equals to x minus 20. So here I will factor the 4 and I will add 4, Okay, means the other side here I will add 4. I'm sorry, 4 times 4, which is 16, plus this is c squared minus 4c plus 4, so I add 4 also here, and then I end up with 4y minus 2 squared plus c minus 2 squared equals to x. Okay, now the basic form of this is y squared plus c squared equals to x. That's r squared equals to x. So if this is the x-axis and this is r, that will look like this is a parabola. Okay, which I rotate in this direction. Now the thing is, of course, then if we go back to here, this is a paraboloid. Centered at 0 to 2. Okay, open to positive x-axis direction. Positive x-axis direction. Okay, can we imagine that? Let's try. So if we have these coordinates here, x is the center is 0 to 2. So this is the center, the vertex, and then it is a paraboloid which opens in the x direction only by half. So it's like it will look like this. Maybe like that. Basically, it's on the skinnier side. Like that. Okay. Yeah, it opens in positive x direction. Now the vertex is 0 to 2 though. Number 36, let's do one more. Number 36, we have x squared minus y squared plus c squared minus 2x plus 2y plus 4c plus 2 equals to 0. Okay, I think I will move the y squared component to the other side. Like this. Okay, now I will complete the square. I will add 1 for this. And this one here, I will add 4, right, to complete the square. And it's 2 plus 1 plus 4. Now the thing is I need to complete the square on the y also though. So let's just do it this way then. Minus 2y plus 1 plus 2. How about that? Like in other words, I combine these two guys here to make it plus 2. Now then I end up with x minus 1 squared plus z plus 2 squared equals to y minus 1 squared plus 2. No. I expect this to be a cone, but no, because we have plus 2, it is not a cone. So the x minus 1 squared, sorry, I don't need to move the y to the right hand side actually. Plus c plus 2 squared minus y minus 1 squared equals to 2. If we see the basic form, that's x squared plus z squared minus y squared equals to 1, right? And this is r squared minus y squared equals to 1. So it looks like this, but then we rotate that in long y-axis. Okay, so this is actually hyperbola with one sheet parallel to y-axis. Okay, parallel to y-axis, centered, quote unquote, centered at 1, negative 1, and then 1, and then negative 2. 1, 1, negative 2. Okay. Number 42, it gets a bit harder because we now will graph two things at once. Sketch the region bounded by paraboloid this and that paraboloid. This one here is z equals to r squared, so it looks like this, right? While this one here is c equals to 2 minus r squared, so it looks like this, so both of them paraboloids. The thing is, can we graph both of them at once? Well, just put things together then. I try, but I don't think it's nicely doable. Let's see. So in 3 dimension, no, there's no one. So we have a parabola with this one here. Oh, too small. Okay, that's the one facing up. And then you have another one facing down. Let me use another color, but the vertex is 0, 0, 2. Okay, so you will see that they actually intersect here. The intersection actually form you will see it actually form a circle. Now, since we already learned at this point, usually we, if you already learned that next section, 13.1, we can actually find the intersection. Okay, we can actually find the intersection. Let's try. So just in reference of, what color do I want to use? In reference to what we have learned in section 13.1, or if you will learn in 13.1, we basically have the intersection of these two paraboloids, c equals to x squared plus y squared, and c equals to negative x squared, negative y squared plus 2, which when I add, if I add, I will get 2c equals to 2, c equals to 1. Okay, so whatever the intersection is, it will be at z equals to 1. Now then I plug that into either one of the equation. Let's say the first equation. We get this is actually a circle with radius 1, right? Okay, so that's a circle with radius 1 centered at 0, 0, 1, okay, on z equals to 1. Okay, so imagine this. When I say z equals to 1, it's actually parallel to the xy plane. Okay, now how to parameterize that? Well, we can parameterize that with vector function rt equals to the radius is 1. So it's like cosine t, sine t, the c part, make it constant 1. Okay, that's for number 42. Let's see, I think this is the last one. Oh, we have more. We have 2 more. Okay, let's see. Find the equation of the surface obtained by rotating y equals to 3y about the x-axis. Okay, so if I have 2-dimensional xy, y equals to x equals to 3y means the slope is 1/3, right? Approximately like this. And if we rotate that with respect to the x-axis, we will get a cone. Is it right? To be more precise, maybe we call that bicone. Okay, now the thing is, what is the equation? What is the equation? Let me borrow x equals to 3y. When I rotate with respect to the x-axis, it means I will change the y into r and then square it. And this is x equals to 9y squared plus 9c squared. Okay. That's for number 44. And then number 50. Show that the curve of intersection of the surfaces lies in the plane. So we just need to show that either x or y or c equals to constant. That's what we need to show. The same case with the last two, this question here. So the intersection of these two surface paraboloids actually lies on a plane. It's actually a circle on plane z equals to 1. Okay, so here to show that it lies on a plane, I need to show that assuming that it is on xy plane or parallel to xy plane or xz plane or yz plane. Okay, of course there's another plane that it may be like the plane may be slanted. Okay, but I think we see later on. Okay, and how do I do that? I think I will take the first equation and the second equation. I kind of like pile them up, and now you see that they are actually like the x squared, the y squared, and the c squared is by a factor of 2, huh? Okay, let's multiply the first equation by 2 and the second equation by -1. Now my purpose is so that later on when I add, they cancels. Oh no, this is 6x. This is 5y equals to 0. Then when I add, I get 6x plus 5y equals to 2. Okay, so this is the plane. So the intersection is on this plane. The intersection is in plane 6x plus 5y equals to 2. Okay, now before I close this section here, I actually want to teach you at the same time how to use GeoGebra. Let me show you where to do that. Give me a second. Let me share with you here. GeoGebra .org/calculator. Now change the graphing here, becomes 3D calculator. Okay, this way we graph 3-dimensional, and you can use this to graph some 3-dimensional graph. Okay, for example, if I do some of them, the one that we did earlier, number 12, 9x squared minus y squared plus c squared. 9x squared minus y squared plus c squared equals to 0. I think that's question number 12. Okay, so that's what it looks like. Yeah, and the thing is, like, you can actually rotate this, right? So this is the view that we usually have, where the x goes to the left, the y-axis goes to the right, and then the z-axis go up. And you can change the color here if you don't like it. Like I click here, and I wonder how. Setting. Hold on. I want to change the color, but I don't know how to. Oh, here. I want to change the color to maybe green. Now it's better, right? Do you see that? Okay. Again, this is actually, you can drag this to see from a different point of view. Okay. Now, by the way, eventually you will see the phrase or the word projection. Like if we project that on xy plane, we basically see that from the top. Notice that it should be like this. Yeah. So notice that this is x-axis, and the one on the top is y-axis, right? And the z is actually coming to us. But if I drag it this way, then you can see better, right? If I see from the left wall, I basically have the x-axis coming to us. Okay, I have the x-axis coming to us. Oh, actually, the x-axis going into the paper if this way, because you see the y-axis actually going positive to the left-hand side, right? Okay. Again, let's see. This is the view that we usually have, where x goes to the left, y goes to the right, and then c goes up. Now that's for the equation from number 12. Let's see equation for I think number 14 is easy. Number 18, 4, 6, negative 16, 1, 16. 4, negative 16, and then the constant here, I make it 16. Oh, what does it look like? Oh, this is what it looks like. Maybe we zoom it out further. Yeah, that's what it looks like, huh? Okay. Can you imagine that? This is if we see from left wall. Basically, this x-axis coming to us. Okay, when x-axis coming to us. Okay, if we try to see from above, this is what it looks like. Okay, now that's for number what? Number 18. Number 21 to number 28, you can try to do it yourself. Number 32, y squared equals x squared plus 4c squared plus 4. Y squared equals x squared minus 4c squared plus 4. Am I copying it right? Plus 4c squared. Plus 4c squared. So this should be plus here. Oh, that's what it looks like. Yeah, so it is hyperboloid in two sheets. If we look back to our notes here, yeah, that's a hyperboloid in two sheets, right? Number 32. Number 34, number 36. Yeah, you could try to play with the graphing, okay? Now, the nice thing is I tried to use NuCalc, but apparently the presentation was not as good. But GeoGebra.org happens to be a free software that you can use on your actually on your computer. It's on internet, okay? But nothing to download. Nothing to download. Let's try with this number 42. Let's try to do number 42. This is for earlier questions here. Number 42, we basically have two equations here. Number 42, z equals to x squared plus y squared. Okay, and then in the second equation, we have, so you just go on to the next one. Z equals to 2 minus x squared minus y squared. Okay, let's zoom in so that we can see better. You see the intersection actually a circle, right? Can you see that? The intersection actually a circle. Let me show you one more. Suppose I want to show the intersection there as space curve. Okay, now the way we type it will be in three-dimensional coordinates, while if you use NuCalc, it will be in factor notation. Supposed to be in factor notation, but I try to adjust with GeoGebra simply because we want to see that. Okay, so it will be three component. We already saw earlier that the intersection will be sine t, comma, cosine t, comma, oops, why it looks like that? No, that's not the way I want. Huh? Why it doesn't want to take my sine t, comma, cosine? Huh? It doesn't want to take it. Why? Oh, cosine t, and then comma 1. So this is the triple coordinate, right? Sine t, cosine t, comma 1. Now the thing is, unfortunately, I need to teach you at the same time how to draw the curve, right? Which we actually already have. We already have that. You see the graph? Okay. Now, but the thing is, like, I need to control the t running from what to what. So, comma t, that's the parameter or the variable, from 0 to 2 pi. Okay. Now, can you see better? Let me change the color of that space curve. The thing is, how do I change the color? Here maybe. Oh, hey. Setting. What's the color? Change it to black. Now you see that? Okay, if you turn around, you see it's actually a circle, right? And how do we know it's radius 1? Let's see from above. You see, that's radius 1. Okay, 1/2, 1, like that. Okay, let's see the last question. Last question. That's a long one. You do it yourself. You do it yourself. Okay, number 50. You tried. I'm referring to this one here, number 50. Try to graph it yourself and see that the intersection is actually on a plane, and that plane is slanted, right? That plane is slanted. So in three dimension, it will look like approximately 3 here. No, it's like this. So it will intersect on this plane. This is x-axis, this is y-axis. Okay, yeah, but you play with that GeoGebra.org, GeoGebra.org, and then calculator. You need to change this to 3D calculator. Okay, you need to change that to 3D calculator. Okay, that's for this 12.6.